R&D teams are currently racing to perfect CO₂-derived recyclable polymers as commercial CO₂-based polycarbonate ether polyols move into industrial production. But a common structural flaw remains in how these materials are developed. In many labs, the initial synthesis of the polymer and its eventual end-of-life recovery are still treated as two isolated research projects. High levels of CO₂ incorporation offer no advantage if the resulting material is too brittle to survive processing or too unstable to be formulated into a reliable product.
OnlyTRAININGS. Learn what works in the industry.
This problem extends to the back end of the life cycle. An efficient depolymerization yield is industrially useless if it results in a highly contaminated chemical mixture that requires expensive multi-stage purification. Building a truly circular material requires a different starting point. Engineers must design the polymer, its mechanical performance, and its specific route back to a usable monomer as one connected, simultaneous development. As these materials move from the lab toward the market, the technical requirement has changed. A material's end of life must be engineered at the same moment the polymer is first created. This circular design window defines the true operational scope of these polymers. It requires moving a material through 7 connected nodes: polymerization, molecular architecture, processing, application performance, controlled depolymerization, monomer recovery, and finally, repolymerization. The bottlenecks begin at the polymerization node. Success depends on controlling CO₂ and epoxide selectivity at the atomic level, forcing molecules into specific structural pathways. Without precise control, side reactions loop back to form cyclic carbonates, ruining the architecture and preventing sequence engineering. Even when synthesis is successful, the material must process reliably in factory settings and meet the mechanical performance standards required for its intended application. Mastering these front-end reactions is a significant technical hurdle, but that progress is negated if the resulting plastic degrades or fails during its service life in the real world. This leads to the recovery paradox. Formulators must build a depolymerization window where the material stays perfectly stable during its everyday commercial use, but then unzips back into monomers the moment a specific recovery trigger is applied. This creates a challenge for additive design. Stabilizers and plasticizers used to enhance the polymer service life cannot be allowed to contaminate or interfere with the recovery chemistry later on. Computational discovery has exponentially multiplied the number of structural combinations we can consider, moving the research far beyond what can be tested manually at a bench. Recent work has identified up to 1 million synthetically accessible candidates for chemically recyclable polymers. This volume changes the central R&D question. It is no longer just, can it incorporate CO₂, but can it be selectively recovered and rebuilt without losing the properties that made it useful in the first place? With 1 million potential candidates and dozens of compounding variables, successful development requires a strategic, closed-loop approach to molecular design. The technical advantage in this market belongs to the R&D scientists and formulators who can master this complete closed-loop architecture. OnlyTRAININGS has developed an advanced expert session specifically for this challenge: CO₂-derived and chemically recyclable polymers, design, depolymerization, and recovery. This training is designed for experienced professionals. We skip the basics of carbon capture and introductory chemistry to focus entirely on the molecular and formulation decisions that determine a material's industrial viability. The curriculum covers advanced reaction control, engineering property retention across multiple cycles, and troubleshooting recovery failures in real-world waste streams. Provides 6 months of ecosystem access, a verifiable training certificate, practical R&D toolkits, and 24/7 access to our Expert Connect forum for technical questions. Stop designing the end of life after the polymer is finished. Click the link in the description to register and start engineering the complete loop today.